In episode 13, titled NAT64 and IPv6 Interop, When It Appears and What Breaks, we treat Internet Protocol version 6 to Internet Protocol version 4 bridging as a controlled compromise because that is what it is in practice. When parts of an environment move to Internet Protocol version 6 only, legacy services and dependencies do not automatically follow. And organizations often need a bridge that preserves reachability without immediately redesigning everything. The exam tends to present this topic as a transition mechanism, but the deeper test is whether you understand what assumptions the bridge breaks and how those breaks show up as symptoms. Network Address Translation 6.4 can be a useful tool, yet it adds state, translation identity issues, and dependency chains that can be brittle when teams are not prepared. Thinking of it as a compromise keeps your expectations realistic and helps you choose answers that acknowledge operational impact. The goal here is to make you fluent in when Network Address Translation 6.4 appears and what tends to fail when it is introduced. Before we continue, a quick note. This audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Network Address Translation 6.4, commonly shortened to NAT64, is the mechanism that translates Internet Protocol version 6 client traffic to reach Internet Protocol version 4 only destinations. The client speaks Internet Protocol version 6, and the destination speaks Internet Protocol version 4. So the translation device sits between them and rewrites addressing so both sides can communicate. From the client perspective, the destination appears as an Internet Protocol version 6 address, but that address is typically a representation that points toward the translation gateway. From the destination perspective, the connection appears to originate from an Internet Protocol version 4 address associated with the translation device, which means multiple clients may share that translated identity. NAT64 relies on state tracking to keep sessions distinct, and it often behaves similarly to other translation patterns in how it consumes ports and maintains mappings. In exam logic, NAT64 is usually presented when the scenario says clients are Internet Protocol version 6 only, but must reach Internet Protocol version 4 resources, and the question is testing whether you understand the translation boundary. The best answers acknowledge that reachability can be achieved, but they also account for the consequences in logging, policy, and application assumptions. Domain Name System 64, commonly shortened to DNS64, is the companion mechanism that synthesizes Quad A answers when only an A record exists, and it is often what makes NAT64 feel seamless to clients. When a client requests a name, the resolver can return an Internet Protocol version 6 address even if the original service is only represented by an Internet Protocol version 4 address in the domain name system. The synthesized Quad A record typically encodes the Internet Protocol version 4 address in a form that directs traffic toward the NAT64 gateway, allowing the client to initiate an Internet Protocol version 6 connection as usual. This is why NAT64 and DNS64 are frequently discussed together, because without synthesized answers, the client may not know how to reach an Internet Protocol version 4 only service using Internet Protocol version 6. The silent nature of this synthesis is also why some failures are surprising, because clients behave normally while the network is doing extra work behind the scenes. In exam scenarios, when name resolution is part of the path, DNS64 is often the hidden dependency that determines whether NAT64 works at all. A common use case is an Internet Protocol version 6 only network reaching legacy services, and this often occurs in environments that are constrained by address scarcity or that are deliberately simplifying internal addressing. An organization may deploy Internet Protocol version 6 only in a new segment, such as a new campus network, a new cloud virtual network, or a managed device fleet, while still relying on older Internet Protocol version 4 services for authentication, updates, content delivery, or partner integrations. NAT64 becomes the compromise that allows the new segment to function without waiting for every legacy dependency to be modernized. This can be especially attractive when the organization wants to avoid running dual stack everywhere, because dual stack doubles policy and monitoring complexity. The exam tends to frame this as a transition bridge, where the key is choosing between coexistence options based on operational maturity and dependency realities. NAT64 is most compelling when the client environment can be controlled, and when the set of legacy destinations is understood and stable. One of the first things to warn about is that literal Internet Protocol version 4 addresses bypass DNS64 and fail because DNS64 only helps when names are used and resolved through a DNS64 aware resolver. If an application is coded to connect directly to an Internet Protocol version 4 address, or if a configuration file contains a hard-coded address, there is no name lookup for DNS64 to synthesize. In an Internet Protocol version 6 only client environment, that literal Internet Protocol version 4 destination is not reachable directly, so the connection fails even though other applications using names work fine. This failure mode is common because many legacy systems, scripts, and embedded devices still use literal addresses for simplicity or historical reasons. The exam often hints at this with symptoms like web browsing works but a specific application fails, which should trigger suspicion about literal addresses or non-standard name resolution behavior. The key lesson is that NAT64 is not a universal fix for all Internet Protocol version 4 dependencies. It is a fix for those dependencies that are accessed through name resolution compatible with DNS64. Logging challenges are a major operational consequence because NAT64 changes how you link Internet Protocol version 6 clients to translated Internet Protocol version 4 sessions. From the Internet Protocol version 4 destinations perspective, the source may appear as a shared address belonging to the translation gateway, which hides the individual Internet Protocol version 6 client identities. To attribute an action to a specific client, you often need translation logs that record the mapping between the Internet Protocol version 6 source, the translated Internet Protocol version 4 source, the port information, and timing. Without that mapping, investigations can stall because many clients may appear identical to the destination service. This is not just a security concern, it is a troubleshooting concern, because you may need to know which clients experienced failures or which clients initiated unusual traffic. In exam scenarios that emphasize auditability, forensics, or accountability, NAT64 solutions that ignore logging implications are often incomplete. A sound design treats translation logging as a requirement, not an afterthought, and includes retention and correlation considerations. Applications can also fail in less obvious ways because embedded addresses inside payloads do not always translate cleanly, which is a classic pitfall when translation is introduced. Some application protocols include literal addressing information within the application data, such as callbacks, embedded links, or control channels that reference addresses directly. When the transport-level addresses are translated but the payload addresses are not, the destination may attempt to connect back using information that is no longer valid in the client's protocol world. This kind of failure can be inconsistent because it may depend on specific features, specific modes, or specific server behaviors, which makes it easy to misdiagnose. It is also a reason why some applications appear to work for simple tasks but fail for complex workflows that involve secondary connections. The exam may not ask you to name specific protocols, but it often expects you to recognize the general pattern that translation can break application assumptions beyond basic connectivity. The safest mental model is that NAT64 preserves reachability for straightforward client-to-server flows, but it can struggle when applications embed addressing or expect symmetrical connectivity. Firewall policy must account for translated address forms because translation changes what security controls see and what they can match on. On the Internet Protocol version 6 side, policies might be written in terms of Internet Protocol version 6 source and destination addresses, and they need to allow clients to reach the NAT64 gateway and the synthesized destinations. On the Internet Protocol version 4 side, policies might see traffic originating from the translation gateway's Internet Protocol version 4 identity, and if rules are written expecting distinct client sources, that expectation can be broken. This also affects rate limiting and reputation policies, because multiple clients can share a single translated identity, making per-client enforcement harder at the Internet Protocol version 4 boundary. Stateful inspection behavior matters too, because return traffic must be allowed consistently across both sides of the translation boundary, and mismatches can create one-way failures. In exam reasoning, the best answer often includes the idea that security controls and policy enforcement must be aligned with translation behavior, not simply copied from a non-translated design. Translation is a boundary, and boundaries demand explicit policy thinking. Consider an example where a mobile client on an Internet Protocol version 6 capable network reaches an Internet Protocol version 4 web service, because this illustrates how NAT64 and DNS64 can make legacy access appear normal. The client requests a website by name. The DNS64 resolver returns a synthesized Quad A record, and the client initiates an Internet Protocol version 6 connection to that synthesized address. The NAT64 gateway receives the traffic, translates it to an Internet Protocol version 4 connection toward the legacy web service, and maintains state so responses can be mapped back to the client. To the user, the site loads and the connection looks like any other, which is why NAT64 can be attractive for consumer-like access patterns. The hidden complexity emerges when you need to troubleshoot a failure, because the path now includes name synthesis, translation state, and policy on both protocol sides. In exam scenarios, this is why troubleshooting and logging considerations often separate a merely plausible answer from the best answer. A strong troubleshooting queue is when only certain applications fail consistently while general web access works, because that pattern often indicates a dependency that does not use DNS64 or that embeds Internet Protocol version 4 assumptions. If the failing application connects to a literal Internet Protocol version 4 address, it will fail in an Internet Protocol version 6 only context, even though name-based services succeed. If the application uses a custom resolver or bypasses the expected domain name system path, it may never receive synthesized Quad A answers, causing failures that look mysterious. If the application requires secondary connections, embedded addressing, or callback behavior, translation may handle the initial session but fail when the workflow becomes more complex. This is the type of pattern the exam likes because it tests whether you can interpret symptoms and infer where in the dependency chain the break occurs. The best troubleshooting answer is often the one that checks name resolution path, confirms whether the app uses names or literals, and verifies translation policy and state rather than blaming the server immediately. When you recognize this symptom pattern, you can narrow the likely cause quickly and avoid chasing irrelevant layers. A practical checklist for prerequisites includes DNS64, NAT64, routing, and policy, because NAT64 success depends on the chain being intact rather than on a single device being on. DNS64 must be in place so that clients receive synthesized Quad A records for Internet Protocol version 4 only destinations they need to reach. NAT64 must be reachable and correctly configured to translate the synthesized traffic into real Internet Protocol version 4 sessions, with sufficient state capacity to handle expected load. Routing must support reachability to the NAT64 gateway in Internet Protocol version 6 space and from the NAT64 gateway to the destinations in Internet Protocol version 4 space with consistent return paths. Policy must allow the traffic across both protocol boundaries, including stateful return traffic, and logs must be available to correlate sessions when troubleshooting or investigating. If any of these elements is missing, the failure can look like the service is down, even when the service is healthy, because the bridge itself is broken. In exam reasoning, correct answers often implicitly satisfy the prerequisites, while incorrect answers propose NAT64 without acknowledging the supporting dependencies. When NAT64 introduces unexpected failures, mitigation choices should be quick and pragmatic because the worst time to debate architecture is during an outage. One mitigation is to identify and fix literal Internet Protocol version 4 dependencies by moving them to name-based access or by updating configuration to use hostnames that can be synthesized through DNS64. Another mitigation is to ensure the failing applications are using the intended DNS path, which can involve standardizing resolvers and reducing split behaviors. If application payload embedding is the issue, mitigation may involve using application-level gateways or adjusting workflows so that embedded addresses are avoided or handled correctly. In some cases, introducing limited dual stack for specific critical systems can be a practical workaround because it restores direct Internet Protocol version 4 reachability for the dependencies that cannot be cleanly bridged. The key is that mitigation should reduce uncertainty and restore service while preserving the ability to move forward with a controlled plan. On the exam, mitigation-focused answers often favor solutions that reduce dependency brittleness rather than piling on more translation complexity. To close the core, consider a scenario where an organization wants to deploy an Internet Protocol version 6 only segment for managed devices, but those devices must reach several partner services that are Internet Protocol version 4 only. And some internal applications are known to use literal addresses. Dual stack would provide broad compatibility, but it increases complexity because both protocols must be secured, monitored, and maintained across the segment. NAT64 would allow Internet Protocol version 6 only devices to reach Internet Protocol version 4 services. But the known presence of literal address dependencies creates a predictable failure mode unless those dependencies are corrected or exceptions are made. In this scenario, the best answer depends on whether the organization can realistically eliminate literal dependencies quickly, and whether it can operate translation with proper logging and policy alignment. If the environment is tightly controlled and the dependency list is understood, NAT64 can be the controlled compromise, but if dependencies are messy and critical, dual stack may be the safer choice despite the added operational burden. The exam is often looking for this kind of judgment, choosing the approach that fits the actual maturity and constraints, not the one that is theoretically elegant. A well-reasoned selection acknowledges what will break and chooses the path with the least operational surprise. In the conclusion of Episode 13, titled NAT64 and IPv6 Interop, When It Appears and What Breaks, the central lesson is that Internet Protocol version 6 to Internet Protocol version 4 bridging is useful precisely because it is a compromise, and compromises have known weak points. NAT64 translates Internet Protocol version 6 client traffic to Internet Protocol version 4 destinations, and DNS64 synthesizes Quad A answers so name-based access can work even when only A records exist. The common use case is an Internet Protocol version 6 only network reaching legacy services, but literal Internet Protocol version 4 addresses bypass DNS64 and fail. And embedded addressing inside payloads can break workflows in subtle ways. Logging and policy must be designed for translation because attribution and filtering are harder when many clients share translated identities, and return traffic and state must remain consistent. Recap what breaks by remembering literals, embedded addresses, logging correlation, and policy alignment. Then assign yourself one dependency recall drill by choosing a single service and naming whether it relies on DNS64, NAT64 state, routing consistency, and firewall policy on both protocol sides. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.